Good morning everybody. In this video I am going to present a lecture on comparison tests. So this is a video lecture for the program BSc and semester 5th semester, subject mathematics, and session 29. So let us start. Improper integrals. In that we see comparison tests. So this is the learning objective. This is the session outcomes. These are the prerequisites, that is bounded function, convergent, divergent functions, and infinite discontinuity. So let us start with comparison test 2. So it states that if f of x by g of x tends to L when x tends to a and L is neither 0 nor infinite, then the two integrals, integration from a to b f of x dx and integration from a to b g of x dx, either both converge or both do not converge. So this is the statement of comparison test 2. So now we prove this theorem. So as we know that since f of x by g of x is positive for all x, so therefore limit as x tends to a f of x by g of x equal to L, it cannot be a negative. So let d be the positive number less than L, so that there exists a number c in the interval a to b. Okay, so assume that d be any small positive number which is less than L. Okay, so then there exists automatically a number c in between a and b, such that L minus delta is less than f of x by g of x, which is less than L plus delta. Now we have for all x belongs to this semi-open interval AC, then we have L minus delta g of x is less than f of x, and f of x is less than L plus delta into g of x, because we have taken a number for x which belongs to this semi-open interval, that is a to c. So when you consider a point x in between a and c, so then this relation holds, that is L minus delta into g of x is always less than f of x, and f of x is less than L plus delta into g of x. So now integration from a to b f of x dx, it is convergent, which implies integration from a to c f of x dx is also convergent, because integration from a to c is a part of the interval a to b. So therefore in the interval a to b f of x dx is convergent, so therefore in the interval a to c f of x dx is also convergent. So which means L minus delta integration from a to c f of x dx converges, implies that a to c g of x dx converges. So which implies integration from a to b g of x dx is also convergent, because a to c g of x dx is convergent and L minus delta is into a to c f of x dx is convergent. Okay, so therefore integration from a to b g of x dx is also convergent. Similarly, it can be proved that integration from a to b g of x dx does not converge, implies integration from a to b f of x dx does not converge. Okay, also we from the comparison test 1 we have proved that integration from a to b g of x dx convergent implies that integration of from a to b f of x dx converges. So which means integration from a to b f of x dx does not converge, which implies integration from a to b g of x dx does not converge. Okay, by comparison test 1 we have proved this. Therefore by using that comparison test 1 we arrived this statement. Okay, so this is about the comparison test 2. So next we see some useful comparison integrals which are very helpful in solving the problems. So those are The first one is the improper integrals, integration from a to b dx divided by x minus a whole raised to n converges if and only if n is less than 1. Okay, so integration from a to b dx divided by x minus a whole raised to n, integral of this form is convergent if and only if n is less than 1. Similarly, the second one we have the improper integration from a to b dx divided by b minus x whole raised to n is convergent if and only if n is less than 1. N is less than 1. Okay, so these are the two important comparison integrals we should remember. Next we see the problems on convergence. So here the first problem is examining the convergence of integration from 0 to 1 dx divided by x raised to 1 by 3 into 1 plus x squared. So solution. Now here 0 is the point of infinite discontinuity, right? In this case 0 is the point of infinite discontinuity. Why? Because if you substitute in this equation, that is x equal to 0, which gives an infinity, so therefore we say that 0 is the point of infinite discontinuity. So now let f of x is equal to dx divided by 1 divided by x raised to 1 by 3 into 1 plus x square, and g of x is 1 divided by x raised to 1 by 3. Now limit as x tends to 0, f of x by g of x is equal to limit as x tends to 0, 1 divided by 1 plus x square. Okay, f of x by g of x means 1 divided by 1 plus x square is equal to 1. Okay, is equal to 1. So as we substitute x equal to 0, this gives x equal to 1. So hence integration from 0 to 1 f of x dx and integration from 0 to 1 g of x dx have identical behavior. So but n is 1 by 3, which is less than 1. So therefore integration from 0 to 1 g of x dx converges by comparison test 1. By comparison test 1, because n is 1 by 3, which is less than 1. So therefore integration from 0 to 1 g of x dx is convergent. So therefore hence integration from 0 to 1 dx divided by x raised to 1 by 3 into 1 plus x square also converges, because we by this condition, okay, by this condition limit as x tends to 0 f of x by g of x is equal to what? Limit as x tends to 0, 1 divided by 1 plus x square, which is equal to 1. Okay, so now by using this condition, if this condition is satisfied, so then we say that both the integrals, that is 0 to 1 f of x dx and integration from 0 to 1 g of x dx, have identical behaviors. Identical behavior means what? If one converges, then other also is convergent. If one is divergent, then other also divergent. So therefore the two integrals behave alike. Okay, so now but n is equal to 1 by 3. As we see in this equation, in this second function, n is equal to what? Here n is equal to 1 by 3. So therefore n is 1 by 3 means it is less than 1. So therefore integration from 0 to 1 g of x dx, it is convergent by that using that integral. Important useful integrals we have seen now. So therefore this is equal to it is convergent. So therefore when this is convergent, we say that because these two behave they have identical behaviors, so when this is convergent, so integration from 0 to 1 dx divided by x raised to 1 by 3 into 1 plus x square also convergent, because both behave both show similar behavior. Therefore we say that integration from 0 to 1 dx divided by x raised to 1 by 3 into 1 plus x square also convergent. Okay, so these are some examples which I left for you to solve. Just try these problems. So the integral 0 to 1 dx divided by x square into 1 plus x square, it is convergent, first one. Second one does not converge. Third one oscillatory, and fourth one none. So try to solve this problem using the comparison test 1 and 2. Okay, and find the convergence of this integral. So here the answer is b. That means it does not converge. Okay, so try to solve this one. Similarly, we have another problem, the integral from 0 to 1 dx divided by x raised to 1 by 2 into 1 minus x whole raised to 1 by 2. It is convergent, divergent, oscillatory, or none. So, okay, so here the answer is A. A means it should converge. So here take this one as f of x, that is f of x is equal to what? 1 divided by 1 minus x raised to 1 by 2, and take g of x as 1 divided by x raised to 1 by 2. Okay, now check the limit. Limit as x tends to this 0, 1 divided by f of x divided by g of x, right? So if it equal to 1, then we say that they both behave, they show similar behavior. So then go for the integration from checking the convergence of integration 1 by x raised to 1 by 2. So now 1 by 2 is less than 1. Here n is less than 1. So therefore this is x raised to 1 by 2. It is convergent. Okay, so just try this problem. Then the answer is what? It is convergent. Okay. Okay, so these are the references. So with this I conclude this session. Thank you.